All right, so now we can talk about graphs of sine and cosine functions. So again, it's going to be equivalent to if we take this unit circle. The unit circle is a big basis in this course. So the faster that we learn it, the easier this course becomes in being able to pop out what sine and cosine is. But so notice if we take this circle, what if we were to break it apart and make it more linear? So in other words, what I really want to do is we took this function right here that we have. In fact, let me switch out of this to show you what's going on here real quick. So if we look at this in terms of PowerPoint, we can kind of see that if we took this unit circle, which is down here at this bottom right, and we actually let theta run between 0 and 360, that it keeps going, it kind of creates these nice curves for cosine and sine. So we basically are just taking this unit circle, and instead of letting it go round and round, we're making it go linear, so that way we can kind of see that it actually creates a nice shape for us and everything. So that's kind of what we're seeing here. So let me switch back over to here now. So that's what we're kind of seeing with these curves, is that it's actually running through, theta's running all the way through this, which is creating a curve for cosine looks like this, and sine looks like this. So it kind of creates the same thing, just in a slightly different way. So if we were to create a table of values, and we were to create all of our basic values between 0 and 2 pi, so we've got 0, pi over 6, pi over 3, pi over 2, 2 pi over 3, 5 pi over 6, pi, 7 pi over 6, 4 pi over 3, 3 pi over 2, 5 pi over 3, 11 pi over 6, and 2 pi. These are just our main angles between 0 and 2 pi. Yeah, they're in terms of radians, so we just have to make sure our calculator's there, or pull them straight from our unit circle that hopefully we already know. If we were to plot each one of these as XY points, notice it creates this nice smooth graph. It has a period of 0 to 2 pi, because what we're looking for is if we have our starting point here and our ending point here, we're looking for where we go through that same value at the same place. It wouldn't be pi, because here we're going up first through 0, and here we're going down. So we have to come back to here. So that's why our period is 2 pi here. So for the sine curve, it does keep going left and right as far as we want to go. It keeps going on forever. We can stop it at certain points in terms of cycles. But some characteristics that we have for our graph is that the domain is negative infinity to infinity. Its range is brackets -1 to 1. It has a period of 2 pi, because that's how long it takes us to go through every value and start back in the same way again. So with these characteristics, it's an odd function as well. So sine of -x is equal to minus sine of x. So we just got to keep that in mind. So these are some main characteristics that we need to look at. And we'll start seeing some other things as we go here as well. So our cosine curve has very similar characteristics, that its domain is negative infinity to infinity. Range is -1 to 1, a period of 2 pi. It is an even function. So cosine of -x is equal to cosine of x. Its period, like I said, its period is 2 pi. It still has the same type of cycle. We can do different cycles left and right. So it's very similar. It's just like a shift. We shifted it left or right like we did back in pre-calculus and college algebra, that we just shifted it and everything with transformations. In fact, here's where we talk about some transformations as well. So those same ones that we did in previous course, we can still do them here with the same type of theory. So notice that if we take and we have a 1/2 multiplier on the outside, all we did was we just vertically shrunk it and everything. If we had a 2 on the outside, all we did was vertically stretch it higher and everything. With numbers on the outside, we're not changing our starting and end point. We're just changing our ranges that we have here. So we're changing our ranges, not anything else right now. But we can sit here and talk about transformations. Like here's a big thing on transformations if we're in this form. So everything that we learned in pre-calculus regarding transforming functions applies right here. So y equals a sine of bx minus c. So therefore, y equals a times sine. If we factored out a b from our bx minus c, if we factor out a b to make this b times x minus c over b, then we can see a lot more stuff from it. The a on the outside is our vertical stretch or shrink, also known as our amplitude. Horizontal shift is the c over b term, so x equals c over b is our horizontal shift. Our stretch or shrink is by whatever factor of b we have right here once we factored it out. Doesn't matter if we're using sine or cosine, they both have the exact same thing. So just like I was talking about, the amplitude of A is the absolute value of A in both cases here. Our starting point is x equals c over b for the sine function because we had a shift over there. So my period is going to be 2 pi over b, no matter which case we're going to do it. It's whatever's in front of our x term there. Amplitude is absolute value of A. There's no shift or anything on our starting point for the cosine. It's just our straight up one. So a summary of our transformations. This will go the exact same whether we're having sine or cosine here. So first we're going to find our amplitude, which is the absolute value of A. We're going to find our period, which is 2 pi over b. Find the phase shift, which is our c over b term. And then find the interval on the x-axis that we're going to do one cycle. That's going to be from our starting point of c over b to c over b plus our period of 2 pi over b. Then we're going to divide the interval into 4 to plot key points. We're going to graph one period, and if we need to, we're going to extend it. So it all just depends on what the problem asks us for, so just be aware of that. Our process is exactly the same for if we had cosine. Everything remains the same except for we just have a different function. So we're going to start out right here by determining the amplitude and everything else we want to know about this in order to graph it. So graph it for 0 to 2 pi for y equals 8 sine x. So let's label everything that we know. We know that our A is 8, our B is 1, and our C is 0. We label that every time, we can easily figure out everything. Amplitude is the absolute value of A, so absolute value of 8 is 8. My period is 2 pi over B. So 2 pi over 1. That's just 2 pi. My phase shift is C over B, which is just 0. So then we could try graphing this. And basically what we're going to do is we want to graph from 0 to 2 pi using values like this right here. Just to kind of show what we're doing here. If we wanted to really know what this graph looked like, what we could do, we could go out here to desmos.com. It's a nice, easy graphing calculator out here. And what I'll do is I will switch and share. All I did was go to Desmos. So now I'm going to type in my function here, which was y equals 8 sine x. And notice that's what we're looking for. If we wanted to plot specific points, so x equals 0. If we wanted x equals pi over 8. If we wanted x equals pi over 4. And notice that these values here, pi over 4, comma 5.657. We have pi over 8 and 3.061 and 0, 0. So all three of these points correspond to my graph up here that we could see this. And we can kind of see how this is graphed. So let's go back to our work here. So we could do the same thing for the following one. Y equals 3 cosine 4 pi over x. So we know in this case, A is 3. B is 4 pi. C is 0. So my amplitude is the absolute value of A, which is 3. My period is 2 pi over B, which reduces to 1/2. My phase shift is still C equals 0 because that's C over B. 0 over 4 pi is still 0. So my interval that we're working from is from 0, which was my phase shift, to 0 plus my period. So that's how we get to 0 to 1/2. We could come back over here and we could regraph this using our new function of 3 cosine 4 pi x. Notice this one has a lot different graph. So what we could actually do here is we could come over here to settings and we could make our x-axis between 0 and 1/2, because that's what our bounds are on. And so we might have to change what values we plug in, because notice we only have one value, and that's the pi over 8 that falls in between that. So we might need to change these values to match what we want to plug in here. So just keep in mind, we may need that. So this one's a little bit different here in terms of what we're doing. So, but we're still going to do the same thing, that our A is -4. Inside of here, what we'd want to do is we'd want to make this, go ahead and make this -4 sine of 4 times x minus pi over 4. So then that way we can identify that B is 4 and C is pi over 4. So my amplitude is the absolute value of A. So absolute value of -4 is 4. My period is 2 pi over B, which is 2 pi over 4 or pi over 2. My phase shift is my C, which is pi over 4. So the interval that I'm working on is pi over 4, comma pi over 4 plus 2 pi over 4. So that gives me pi over 4 to 3 pi over 4. In terms of what our graph would look like in this case, we could jump back over here to Desmos. And we can type in just the way we see the first one. So -4 times sine of 4x minus pi. And we want to come back over here and change our settings. So that way my x-axis is now between pi over 4 and 3 pi over 4. We can see that we do 1 full period here and everything. So that way we can actually see. Now notice that our pi over 8 and pi over 4 values may not fall inside of there anymore. So we just have to be careful of that right there. One last transformation that we can have. Everything remains the same, except for now we can add in a vertical shift of a plus d on the end. We can do the same thing for sine or cosine. That's the only difference in the a, b, c over b and everything is just adding in that d. It works for sine and cosine functions. So vertical shifts, if we start with our standard function y equals sine of x, what you do is you can take each one of them and you add 2 to your y values. For the blue here, we can subtract 1 from the y values for the red and everything. And we can just kind of see that in each case, we either went down or we went up, depending on what we were doing. We go the same on the outside, just like we did in previous transformations. So same thing here. We can define what our A is. Our B is 1/3. Our C is 0. And now in this case, we also need to identify that D is 2. So our amplitude in this case is 3. Our period is 2 pi over 1/3, which is 2 pi times 3, which gives us the 6 pi. For our phase shift, C is 0. For the interval we're working on, it's 0, 0 plus our period, so 0 to 6 pi. And then we can in turn go back over and we could graph this as well using the same exact principles. The last thing we could do is we could try to match a graph. And if we tried to match a graph, what we have to do is we have to kind of see what we're doing here. One, we can still figure out our characteristics. So at 0, we're up here at 2. So we know that our amplitude is a 2. We know it's a positive 2 because we're in the positive. So that gives us our 2 here. Now, where does it get us to? So here, this right here is my period. So my period is pi over 2. So pi over 2 is actually equal to 2 pi over b. So we need to be able to solve for b. So b times pi equals 4 pi by cross multiplying. So therefore b is equal to 4. That gives me my 4 over here. So therefore my function is 2 cosine 4x, because we see how erratic this means. That means that it's going to be going a lot faster than our normal sine or cosine function here. So we just have to kind of be able to look at it and kind of see a few things off of it of what's going on in each case here.